Can everyone hear me okay? Sounds like the mic's on. Great. Well, welcome to the session. My name's Josh. I've joined the Flare team, which is the reverse engineering team at Mandiant, just this past July. Before that, I was with Uppercase Chronicle at Google. Was with that team for about a year. And before that, I spent a decade in academia and a bunch of additional work. I was in the National Guard and did some cyber defense and some other jobs in that field as well. So today's session, I was asked to talk about something technical, and so I'm going to get in the weeds here a little bit with this downloader, where the name came from, why I decided to take a look at it, a little bit of just the typical workflow of dealing with this type of sort of commodity level malware. It is a downloader, which means it's oftentimes sold to others to distribute. Its sole purpose then is to download and distribute other malware. So something like this gets into an environment, it can lead to pretty prolific results because you can have a lot of different disparate families being dropped. I didn't know what the audience was going to be, the background of everyone. So if you have questions, if something doesn't make sense, please feel free to, we'll have Q&A at the end, but please feel free if you want to ask as we go. More than happy to try to answer. I'm planning to talk for about 20 to 25 minutes. I mentioned, though, that I was in academia for 10 years, and I learned along that time to talk ad nauseum. So I got this timer here that'll hopefully keep me on track and not taking away too much from your lunch. So probably the first question to ask is why LgoogLoader? Who came up with the name? I don't know. Oftentimes, researchers or companies that discover these, they come up with the name for some reason. In this case, I guess the name, why they named it what they named it, I'm not entirely sure, but there is a bit of a Google reference here. So that was one thing that initially caught my eye working at Google. I also like to scrape the internet, and I was doing that long before I joined Google because it was more or less a hobby. And what I would find scraping the internet is that I would find what are called open directories. Open directories are just like a folder view of a website or a web server. And inside of those directories, I still find those to this day. You can oftentimes find a whole number of payloads that might be hosted there. So, a malware or a threat actor is getting ready to distribute a number of different files. There they all are, so we can grab them and get them into our system. I was finding at one point in time a lot of toolkits. They'd upload their panels and leave those as archive files and not take them down. So now you could grab the panels and you'd have full insight into how those panels worked. Credentials were there oftentimes, but I'm not saying that I logged into anything. So this is just output from a custom tool that I wrote to do a little bit of scraping. Anything that I find that I think is worth sharing with the community, I would upload it to abuse.ch. Very similar to VirusTotal, except it's a totally open platform. There's no licensing required. So I found it very valuable as a community member not working for a big company to have this sort of information available. So I like to contribute back to it as much as I can. Okay, so initially I did this analysis earlier this year, and I came across these samples that were not being identified. So I was a bit curious. I took the samples, I put it in a sandbox, looked at the network behavior from those samples. This led me to this open directory. Now I'm really curious because it's an open directory. We can see the obvious, the .exes, those are in fact executables. Those are other malware families that this particular downloader was going to then reach out and download. It's downloading from itself, which is kind of odd, but certainly not always the case. But then there was the .cfg, enc, file files. Kind of implies, I think, through the naming convention that it's an encrypted config file, and it certainly is. But downloading those, they're just compressed or encrypted data, maybe both. I wasn't sure at the time. So I became even more curious because I'd like to see what those files contained, and if there was any intelligence we could derive or I could derive from them. I also, again at the time, and I think even to this day, there's not a lot of reporting or information about this particular downloader. So it seemed like there was a little bit of novelty there, although there's new things emerging all the time. So it's somewhat hard to pick something that is maybe novel but not having a significant impact. Malpedia is a great place to go. Usually they have a variety of different resources. If you look for a family or a group, everything that's sort of out there gets indexed here. Somebody adds it as a contribution. And what I found was really nothing direct. There was an article that just referenced this as a downloader, but they didn't have any real detailed information. And the information they had was inaccurate compared to what I was observing, which likely indicates to me that this thing is new and it's just evolving rapidly, maybe early stages of development. So I grabbed some samples, And anyone familiar with the output here, the screenshot or the diagram? I see a few people saying yes. Yeah. So this is output from a tool called IDAPRO. IDA is the interactive disassembler. And what it takes is those executable files, those payloads, looks for the machine code, the ones and the zeros, disassembles that, and presents you with the results. So this is the disassembly. So, arguably the lowest level language that we as human beings typically write and can more easily understand. Each block represents a sequence of code. And then between the blocks then, each block will end with some sort of a transfer, a control flow to the next block. So with these blocks that just flow into each other, it's just code that's jumping to another region of code that's jumping to another region of code. You'll see the diagram up above, there is more paths of flow. So you can think more like loop structures or if structures, different branches based off of the logic. Does this look like anything anyone would write for real life? Yeah, maybe. When I was teaching, maybe I'd see this in some of the intro to computer science courses. Well, I wouldn't see anything like this. But what you're looking at then is intentional layers of obfuscation. So the program itself, when it's executed in memory, it'll just skip through all of these. CPUs now are quite powerful. We have a lot of resources. It doesn't take much if we add a bunch of junk instructions for the malware authors to waste CPU cycles. When we as humans want to look at it or even try to build tools to automate this, and we run into these obnoxious chains, I call them jump chains. There's probably a more formal definition for them, but I couldn't find anything. You can see that it just makes our analysis a lot more difficult because there's all these unnecessary and superfluous unconditional jumps, from a jump to another block, which is a jump to another block to a jump. So it just turns into these big, long functions that are just hard to analyze. One of the techniques, though, when looking at this sort of obfuscation is to try to find where it all ends. And usually oftentimes there are pretty clear indications or patterns or things that you can look for. In this case, you can see the primary diagram. There's a call to EBP plus var4. And if you're not familiar with this convention and assembly syntax, this is just saying that there's a local variable that holds a value, var4, and it has to represent an address because a call instruction tells the CPU to go to that memory location. The fact that it's being dynamically constructed would indicate then that there is a next thing. It's the next stage that we're moving to. Maybe it was some memory that was deobfuscated and staged in memory, and then now we're executing that. Or perhaps it's just some dynamically computed address that now we're following. Tools like IDA, what happens when they disassemble is they're doing it all statically. It's not running the program because that's what we typically use a debugger for. And so when IDA can't tell where that call location is, then it doesn't necessarily go there in order to do the disassembly. So it makes our work just a little bit harder when looking at it in a tool like IDA. So these are good indications. And in a situation like this, I probably transition to a debugger, let the program run so I can observe what's happening, set a breakpoint at that location so we can tell the CPU to stop here, and then just understand what's going on. Maybe we're on to the next stage, which was the case. Now, usually, when you have something like this, you have multiple stages of not only delivery, but then obfuscation of the binaries themselves. And that's what makes analyzing the binaries and automating the analysis of the binaries complicated. So that first layer was just a bunch of that stuff in order to load another executable in memory and then begin execution. So that call instruction that I was just talking about, that actually was taking us to this thing in memory here. And the address is off to the left, 3A2C020. So that's just a virtual address. It's just a way to use hexadecimal notation to understand where in memory something is located, data or code or something. In this case, it's code. What was interesting about this sample is, though, that this is, again, a pretty well-known technique, that it was staging an executable in memory and then beginning execution at the beginning of the executable. That's very uncommon. That's very non-standard. Typically, with a file, when you load an executable into memory, there's a defined entry point. And the operating system loads it, and it says, OK, I'm going to parse all this metadata. I'm going to find the entry point. We'll Once everything's loaded, we'll begin execution, tell the CPU to go to the entry point. So telling the CPU to go to the beginning of the file, where all the metadata is located, is quite odd. Turns out, what this was doing was essentially loading itself. Because when anything, well, malicious or not, when anything, a program takes and tries to load, in this case, another program on the fly, it doesn't have the benefit of the operating system doing the loading for it. So in this case, it has a loader that it built in. The beginning of the file transfers control to the end of the file, which is called an overlay in the PE format specifics. And all of that then gets executed, and it loads this thing into memory, resolves all the libraries and the functionality that it needs, resolves the start address, and then it jumps to that location. Anyone have any questions right now? That's a great question. It's hard to say sometimes. You can oftentimes take each stage and run different signatures across it to try to identify the compiler or the assembler. I can't remember with these if I detected an assembler. Probably the thing that does the obfuscation was probably written in assembly, and then you give it an executable, and then it spits out this kind of garbage that we have to deal with. So I would say most of these protectors, packers, obfuscators are a tool chain that somebody's developed, and either they sell it as a service or however they're distributing it. I, as a customer or criminal actor, I would give them my executables, and they would spit out all of this. So, but to get to this level of, because oftentimes to do, in assembly you can pretty much do whatever you want within the confines of the operating. A higher level language like a C or a C++ sort of constricts it a little bit. So a lot of times you see this stuff, yeah, it probably was written in assembly. And there's a lot. Like every slide here, we could probably spend hours talking about specific things depending on the level of knowledge needed. If we were all on a reverse engineering team, we would want to go into all of the details here and figure it out. Maybe not. Like the overlay stuff, this is the loader. I don't know. If I don't need to know how a loader works, I just need to realize that this is making this thing executable, this next stage, then I can just skip on to the next stage. The thing I do need to know is where is the entry point. So if I dump this thing from memory and I want to reverse it, I need to know where the entry point begins. So I might have to trace into this a little bit in order to figure that out. But I usually don't get into all the details because I don't need to know how all of this level of operation is working. I just need to get to that next stage. Because at this point, I've been talking for 15 minutes, this is just a simple downloader. We haven't even started talking about downloading capabilities yet. Other questions? Okay, so that's just some code from the overlay. I did take a look at it in disassembly, and I just sort of eyeballed some things that made sense to me. Oftentimes, my approach to reversing is doing just that. I take something that I'm not familiar with, and I just try to set kind of mile markers or flags, or just build an overview of where certain important events are happening, and then narrow my focus of research on those areas that I'm the most interested in. Okay, so after this talk, I'm going to be selling art out in the main hallway. And this is going to be part of that art, because I think some of these graphs that IDA produces are really kind of, with the right color scheme, I think they'd look pretty good. Yeah, the Smithsonian Spears. Anybody know anybody from the Smithsonian? Maybe you could hook me up. Again, these are graphs. These are actual blocks that contain an arbitrary number of instructions, and then the yellow, or the green and the red, are just this flow arrows. So the function more or less begins up at the top, and then you can see just it gets convoluted very, very quickly, right? So being able to dissect this and run through it and figure out where the next step is can be a bit challenging. One of the things that I didn't anticipate with this much code is it actually slows IDAPRO down. And so even just scrolling through the graph, it's like, I don't know, like a Windows experience from the XP days. It could get really bad. I worked with a colleague. He wrote a tool, so IDA is extensible. We can do things with this database of code that IDA creates for us. And he wrote something that went through there and removed all that junk. So he took the code from the left and turned it into the code on the right here. Still kind of gnarly, but it looks a lot better than all of that stuff there. Again, down at the very bottom, that's where all the code really was. And so eventually you can look for grep, search, whatever, identify sort of those key areas where you see that next stage transition. And there's certain Windows functions that get called. In this case, it's going to allocate another region of memory. It's going to unpack another executable, and then it's going to execute that. And so I was looking for those signatures and those signs down there, and then I used debugging to set breakpoints and see what was happening, because I was just too impatient to try to sift through all of this code, and even filtering out what was junk and what was real can take some time. Okay, certainly letting things like dynamic analysis help with your analysis, right? So I throw this in a sandbox, and I see eventually the main process is on the top, and an additional process, install util.exe, gets launched. And the path, if you look at, looks like it's coming from, and is coming from, a legitimate Windows path. What I suspect is happening here then is that process, that image is getting loaded from the operating system so that it comes from a legitimate path, and then it's hollowed out and new code is injected in. So it's a really common technique, process injection, process hollowing. From a forensic perspective, it might be harder to pick up on that, other than, does it make sense that this thing launched install util.exe? I don't know. But in this case, that code has been completely removed and replaced with this downloader. So that's another thing that can be really helpful, because then you have these clues when you're looking at the file to say, okay, if I see the Windows functions that typically are used to do this process, or I see the creation of install util.exe, I know I'm getting close to what is hopefully the next stage, maybe even the final stage. So when it comes to analysis for me, I don't typically hold back unless there's a reason that I have to. This led to another stage. There's really nothing to worry about here. It does simple things like, you'll notice the characters at the very top of this, they are just XOR'd in a loop. It's a little hard to see, but down towards the bottom, there's an XOR instruction. It's a really simple mechanism for manipulating bits. If you take some data and XOR with a key, you get some ciphertext. If you XOR that with the same key, you get the original text. So it's a really cheap and easy way for malware authors to hide strings without having to waste a lot of CPU. So those were just important strings to help resolve the path for that install util, get that full path up, load that executable, and then finally inject the final stage. This was kind of a letdown, because after all of that work, the final stage had very little in terms of obfuscation. This is the decompiler. So IDA has both the disassembler, which is the assembly, which is what mainly we were looking at, and then the decompiler, which you pay top dollar for. This gives you something that's a little bit higher, more like a C-like language. But you can see, and probably make a big argument, that this is a lot easier to read than things like this. But if you're looking to learn, I would say start here. And then this is just a bonus. There was some anti-analysis in here. So as you can see there's an if statement kind of in the middle-ish. There's some anti-analysis checks, pretty common. It was looking for different artifacts, virtual machine environments, and some other things. I can't remember now all the details. But it was all pretty basic stuff. Oftentimes, they lump this. Malware authors tend to lump this into one function. Like, here's a function, let's call it, let's check everything that we can think of when it comes to anti-analysis, and then return either a yes or a no, or a true or a false. We're being analyzed. Depending on how that went, then it would try to download the config. And that was the main objective here after passing those anti-analysis, was simply reaching out to the C2 host, you can see at the bottom, grabbing one of the config files, downloading the config file, and decrypting it, and then processing all of the URLs that was in that config file. Now, this is mislabeled. When I first went through this, I didn't dig into all of the functionality. And so I kind of did my hand wavy. I saw a bunch of XORs, and I just called it an XOR loop. Turns out it just used RC4. So that is the RC4 key that is used to decrypt the config files that come from that host. Hard-coded. That doesn't mean that they can't spit out binaries with updated C2 and updated RC4. This actor doesn't do that. They use the same RC4 key for everything. Okay, so I spent some time working with the Suricata project. So I always like looking at network traffic, and this is a great one that I think has opportunities for network-based signatures. It does this pattern of checking using a head request. It has a hard-coded user agent of Chrome, which also would probably stand out in a network, and minimal HTTP headers before it finally issues a GET request. Similar user agent, similar minimal headers, throws in a range header. I don't know why, because it seems superfluous, and then you get the config data. So some really good network traffic here that would be really strong signatures if they're not out there already. And here we go, finally, we get to the config. So how does this have to do with Google? Well, that little blob of text there, that's from Google's terms of use, or privacy policy, one of the two. So that's the only connection, and why it's in there, I can't say for sure, unless they think that it was meant to, when this was decrypted in memory, maybe throw somebody off because they might see that it's the Google terms of service. I'm not entirely sure. But from there, it's just an arbitrary list of URLs. And the functionality processes each one of these, downloads it, and executes it. And then it moves on. So you can see in this case, I didn't go through and label all of these. I don't remember what they were, but a lot of commodity stuff. If you're dealing with malware on a daily basis, you probably would recognize other loaders as well. So you might have multiple loaders now coming into the environment. So if someone were to grab all of those configs, it might look something like this. Again, the beauty of an open directory is you see everything that's there. So it's very easy to go through that open directory and grab each one of those CFG encrypt files because they use the same RC4 key. We can decrypt all of the files and grab all of the payloads. You'll see a number of different places. Again, if you're looking at where stuff's coming from, probably no surprises here. A lot of Discord, the CDN at Discord, probably a good deal of compromised websites, a number of direct IP, so probably some intentionally hosted infrastructure. IP logger request, I'm guessing that's all part of their tracking, so they know, I guess they have statistics. Oh, I guess I did. I do have a little bit on VirusTotal, right? So I think it is interesting and also challenging to try to take the downloader itself and figure out what is it downloading and get very discrete or concrete names to say, oh, LgoogLoader is responsible for dropping all of these families. And so some of the research using VirusTotal, because for the first time in my career I have unrestricted VirusTotal access. I have a number of Yara rules that I've written both for the different stages of the packer, the unpack code. I can do things like live hunts and retro hunts and try to map out the relationships just to see not only what is it distributing, but is it distributing things that we don't know about? Because I think that has some interest and some value to it as well. So some things that happen along the way, especially if you take time, in this binary, when you get to the final stage, the code was a lot clearer, it's a lot more straightforward. And so it was a little bit easier to recognize some functionality that they weren't particularly exercising. For example, in those config files, they can embed an RC4 key in front of each URL and then encrypt those payloads. So right now, when it downloads these things, you've just got executables coming into your network, and they're easy to identify. You'll notice that a fair chunk of these are probably not even over a TLS session. So PE files coming in, I don't know, I'm sure you get a lot of those though. But they could encrypt those now. And the config file, the RC4 key could be used then to, more coordination on their end, because then they have to distribute their payloads already encrypted, but that would make them a little bit harder to detect, at least the presence of a PE file. It also had some additional capability for process injection, so it dropped this benign program and could inject itself into that. So it had a number of different, it didn't persist ever, but it had a number of different ways in which, as those stages were unraveling to get to that primary, the downloader logic for getting itself executed in memory. Some lessons learned. So one of the things that helped me the most, if anyone is doing any sort of debugging on a regular basis, Microsoft has released time travel debugging with WinDebug, and it provides a full trace of the execution. It's not perfect, but what's great about it is then you have a trace file that you can go backwards and forwards. So something like this that's really convoluted, if I got to a point where I was analyzing some code, and let's say I set a breakpoint and then it doesn't actually go there, in a normal session, I'd probably have to restart and work my way back to that position or create snapshots. It just gets kind of be a hassle. With time travel, you just have to go backwards. So it's a really cool feature. If you're doing any sort of analysis, I definitely recommend looking at time travel debugging and just working with WinDebug. It's not everybody's favorite debugger, but it's not bad. And don't forget some of the basics. I had a whole write-up on this algorithm before I recognized that it was RC4. So I did not take a step back to see, I guess, the forest from the trees. And I would have saved myself a whole lot of time if I just would have thought, oh, it's RC4. And I know the algorithm, here's the key. I could have tested that very easily, but it just didn't dawn on me. So I got lost in the weeds and wasted way too much time. Questions? That's all I have on this one. So yeah, lots of stuff we could talk about, but that's just sort of a typical downloader and a lot of the different stages and layers and obfuscation that you'll encounter.
How long did it take you to install this thing?
It took a while. Yeah, those first couple stages of really trying to figure out what they were doing, because I wanted a little bit of insight, but I didn't want complete insight. It took a while, yeah. I can't say how many hours, probably a week's worth of work. Yeah, not quite. Yeah, and there's plenty of rabbit holes, the YAR rules and some of that the scraper that I wrote, some of that stuff too really added to it, but it was interesting. Other questions? Okay, well, I hope everyone enjoys lunch. Keynote's at 2, so I'll stick around if anyone has questions for me. Otherwise, hope you enjoy the rest of MWise. And thank you for your time.